Welcome to part 10. We are marching on forward to completing all of the instructions on this instruction set table. So for this episode, what I want to do is implement this quarter of the instruction set. These are all of our arithmetic operators between two registers. And on the 8080 and Z80, the way it works is every arithmetic operator from hex 80 to BF implies having the A register as your destination register, and the register that you actually write out here is your source register. So just to kind of quickly summarize it, so add B really means register A equals register A plus register B. Add C is register A equals A plus C. Sub B is A equals A minus B, right, so on and so forth. So nice in the fact that all these arithmetic operators are pretty much all the same because they all take one argument and they all use that same register calculation as we did for the moves. So I'm going to get you started with maybe one or two of them. And then for homework for this part of the workshop, you will implement the remainder. The other nice thing is every single one of them is 1 byte in size. So you really can, for the most part, copy and paste a good amount of this. So let's start with add, since that's the first one that we see. So I'm going to say add is going to be hex 80 plus register offset, right? B, C, D, E, H, L, M, and A, just like we saw with the moves, and the pattern is exactly the same. So our add instruction, by now we should know what our boilerplate looks like. And so what do we need to do? What do we need to check? We need to check that the first argument is not empty, but that the second argument is empty, right? There's no comma, something else for any of these arithmetic instructions. It's just the instruction and then one argument. So we want to make sure that the first argument is not empty and that the second argument is empty. And then what action do we want to take? Well, we know that all of our arithmetic instructions are 1 byte in size. And then for add, it's going to be hex 80 plus our register 8 function for our one argument. And that's it. That's all you need. So let's do ADC just to kind of show the pattern here. And again, we can just copy and paste because it's going to be very easy. So what's the first byte that corresponds with an ADC instruction? Well, it's 8 something, 8, 8. So the formula for ADC must be hex 88 plus the register offset. It's exactly the same. We want to check to make sure that our first argument is not empty and our second argument is empty. And then all we have to do is change the starting byte for the output from 80 to 88. All right, let's do sub as well, just to kind of hammer home the pattern. So sub starts at 9, 0. Okay, so let's say that, hex 90, and then our register offset. So same thing, we want to check to make sure that we don't have an empty first argument, but we do have an empty second argument. And then all we have to do is change the starting output byte from hex 80 or hex 88 to hex 90 for the sub. And that's it. So I'm going to leave it up to you all for homework to implement SPB, ANA, extra, aura, and compare. Again, it's exactly the same. You can copy and paste just like I did. Just remember to change your starting byte and change the name of your function. All right, and with that, we will save our work. Add 2 register arithmetic instructions. And I will see you on the next episode.